Hello participants, in this video we are going to discuss the solution to the problem the wizard and his magic potions. In this problem it is mentioned that a wizard makes magical potions using special ingredients. An ingredient has a power level and an ingredient is called special if its power level can be written as a sum of distinct non-negative powers of m. For example, in the problem, so a ingredient can be called a special ingredient. So every ingredient has a power level. Every ingredient has a power level. If this ingredient can be expressed as the sum of distinct non-negative powers of m. For example, suppose the m it is the m raised to I plus m raised to j plus m raised to k and so on is equal to power level, then the ingredient who has this particular power level will be called special. So this ingredient which has this power level will be called special if this power level can be expressed as a sum of distinct non-negative powers of m. So this I, j, k are distinct, and if power level can be expressed in this format, the ingredient which have this particular power level is called special. So I will give you some example. For example, suppose the power level that they given us is, for example, the power level is equal to 65 is the, and suppose m is equal to 4 is the ingredient which have this particular power level special. So let us see. So when we check there, we can see that 65 can be expressed as 4 raised to 0 plus 4 raised to 3, which is equal to 65, where 4 raised to 0 is 1 and 4 raised to 3 is 64. So it will be equal to 65. So we can see that the power level can be expressed as non-negative distinct powers of m. So the ingredient which have this particular power level is special. Another example is, suppose power level is equal to 37 and m is equal to 3. We can see that we can express 37 as 3 raised to 0 plus 3 raised to 2 plus 3 raised to 3, which is equal to 37, where 3 raised to 0 is equal to 1, 3 raised to 2 is equal to 9, 3 raised to 3 is equal to 27. This is equal to, the sum of all this is equal to 37. So this power level is also, the ingredient which have this particular power level is also special, right? So, and in the problem, it is mentioned that we have to find the pth power level of a special ingredient using base m when the power levels are ordered in ascending order. So we have to form all the power levels that we can form using this particular base m, and we have to order them in ascending order, and we have to print the pth power level out of all the power levels that we have ordered in ascending order. For example, if suppose the base that they give us is m is equal to 3, if the base is equal to 3 and m is equal to 3, the power levels ordered in ascending order is as follows. So the first power level will be equal to 3 raised to 0, because that will be the smallest power level that we can form using the base 3. The next smallest power level is 3 raised to 1 is equal to 3. The next smallest power level is 3 raised to 0 plus 3 raised to 1 is equal to 4. the next smallest power level is 3 raised to 2 is equal to 9. The next smallest power level is equal to 3 raised to 0 plus 3 raised to 2 is equal to 10. The next smallest power level is 3 raised to 1 plus 3 raised to 2 is equal to 12. The next smallest power level is 3 raised to 0 plus 3 raised to 1 plus 3 raised to 2 is equal to 13. The next smallest power level is 3 raised to 3 is equal to 27, and it will go on till infinity. So these are the power levels ordered in ascending order using the base m, and using the base m is equal to 4. These are the power levels that we can form, and these are arranged in ascending order. The power levels will go on till infinity, but I have only written some of the power levels. And if suppose they give us a position p, suppose they give us a position p, and suppose p is equal to 5, so we have to print the pth power level from these power levels that are ordered in ascending order. So from this power levels, the fifth power level, the pth power level is 10. This is the fifth power level, that is equal to 10 for m is equal to 3. Now how can we find the relationship between p and this value? How can we output this? Like obviously we can't find all the power levels of m and order it in ascending order and directly print it. It won't be feasible, and it won't fit within our constraints. So we have to come up with some clever approach to print the pth power level of this particular base m. So what we can do is that we can express, I will show you an observation. This is the main observation that you have to come up with. This is the main observation of the problem. So when we express 5 in binary representation, what will be the result? 5 is equal to 101. This is the binary representation of 5. And if you write it in base 2, if we write it in base 2, what will be the value? It will be 1 into 2 raised to 0 plus 0 into 2 raised to 1 plus 1 into 2 raised to 2. So 1 into 2 raised to 0 is 1 plus 0 into 2 raised to 1 is 0 plus 1 into 2 raised to 2 is 4. So 1 plus 4 is equal to 5. This is the base 2 representation, right? So when we simplify it, it will be equal to 2 raised to 0 plus 2 raised to 2. This will be the base 2 representation of 5. Now can you notice something? Can you find a similarity between this and this? We can see that the only difference between this and this is the base. So here the base is m, and here the base is 2. Here the base is given as 3, so we wrote 3, and here the base is equal to 2. So this is the main observation. So for this as well, what is the fifth value? Fifth value is this one, 17. This is the fifth value. 1, 2, 3, 4, 5. This is the fifth value. And you can see the similarity, right? 2 raised to 0 plus 2 raised to 2, 4 raised to 0 plus 4 raised to 2. The only difference here is that the difference in base. Here in the base 2 representation, here the base is 2, and here in the base m representation, base is m. So this is what we have to do. For the value p that they will give us, we need to first express it in the binary representation, and we have to convert it using this base 2 representation. So when we are converting it using this base 2 representation, just replace this base 2 with the base m that they will provide us in the question, and just output the answer. So here if we replace this base 2 with the base m, we will get the answer as 10, and 10 is the answer for this particular pth position. So this is the main essence of the problem, and this is the only observation that we have to come up with to solve this particular problem. Now I will show you the code to how to code on how to solve this problem. So I will show you the implementation for the problem now. So this is the implementation for the problem. The implementation is very easy. The main part of the code is only this much. This power function is used to find the power, and the algorithm that I have used here is binary exponentiation. Binary exponentiation is an efficient way to compute the power. It is much more efficient than just using a for loop to compute the power. I'll add a video on how binary exponentiation works. You can watch that if you don't know what binary exponentiation is. Why can't we use the inbuilt power function in C++? Because the inbuilt power function in C++ may give some small irregularities when we use it to find the power for higher values. That's why that is why I implemented my own power function over here. So this is the main part of the code. Here I am inputting m and I am inputting p. M is the base m and p is the position that we have to find, and I want to store the answer in this variable called answer, and inside this for loop I am iterating from 0 to 31. What this basically does is it iterates from the 0th bit to the 31st bit, and we are going to iterate through the bits of the p. So we are gonna iterate through the binary representation of p, and if at a bit I, if the binary representation for p is set, if p has a value 1 or it is set at the ith bit. A set bit is a bit which has value 1. A non-set bit is a bit which has value 0. So if at the ith bit, if p is set, then we are gonna swap the base. So we are gonna add to answer power m raised to I, where I is the bit position that we are considering. So m raised to I, we are the power of m raised to I we are adding to the total answer. So for in the representation, so as we have explained in the explanation, to find the pth position of the power levels of base m when ordered in ascending order, what we have to do is that we just have to swap the base 2 with the base m, right? So that's what we are doing over here. For the bits that are set in p, we are adding power m comma I to total answer, because the set bits will be the position where p has a power of base 2. So this is the explanation for this code.